The title of my thesis is THz Modulation, Spectroscopy, Device Development, and Material Characterization. So my presentation will cover the following areas. First is the motivation to improve THz technology. Next is faster speed THz phase modulator based on liquid crystal materials. The next is the conductive interface to the internal reflection geometry. Next, I will introduce I explored a metal wire grating in TIR geometry to achieve an achromatic polarization conversion. In the end, I will introduce THz spectroscopy and material characterization in TIR geometry. So the first part is my motivation to improve THz technology. THz is a growing area, but still has challenges in this area. So my research is to address these challenges. THz actually matches with molecules vibration modes such as hydrogen bondings, molecular rotations, and bendings. So THz can provide the information of molecule structure. And THz can also be used in communications to provide ultra-high-speed wireless connection. And THz can also look through many packaging materials such as plastic or ceramic. So THz can be used for the quality control of product. And THz can also look through our clothes, paper, and so THz can be used for security checking. But in THz area, there are still some challenges, such as for the THz phase modulators. This THz phase modulator based on metal material structure, and this device can provide 30-degree phase change at a single frequency. But this kind of resonant effect give very high insertion loss, but the advantage is high operation speed. So in order to improve the phase change, a metal material structure based with graphene and gated with ion gel was proposed. This device can provide 180 phase change, but with very high insertion loss and very slow operation speed because of the ion gel. Another approach to produce phase change is using liquid crystal, because some liquid crystal molecules has birefringence in the THz frequencies. So this device can provide a 60-degree phase change and with low insertion loss because liquid crystal is not based on resonant effect. But the drawback of liquid crystal device is the slow operation speed. There are some challenges in the THz amplitude modulators too. THz amplitude modulators are important for THz comparative sensing imaging. So this structure uses a patterned PCB board to specially modulate the THz signal for comparative sensing imaging, and by mechanically change different pattern PCB board, so the THz signal can be specially modulated. And this kind of design can be used in the THz time domain system, so it can acquire both phase and amplitude information, and it has very high signal to noise ratio. But it's a mechanical way to change the pattern, so the operation speed is quite slow. Another kind of THz spatial modulator is use metal material structures. And the metal material structures can only acquire amplitude information, and because the modulation depth is very slow, so it has low signal to noise ratio. But this kind of design is electric control, and it has fast operation speed. Another approach is using photo-doped silicon by using a DMD to generate a patterned optical pumping pattern on the silicon substrate, so we can spatially modulate the THz signal. And this kind of design can be used in the THz time domain system, so it can acquire both amplitude and phase information. But the modulation depth of this design is low because of the transmission geometry. And the advantage of this design is it can be easily expanded to a large area pattern by the DMD device. And DMD device has like megahertz frame rate nowadays, so it has fast operation speed. So in general, the desired features for THz modulator include high modulation depth, broadband performance, high operation speed, low insertion loss, and should be easy to scale to array. So my research is to address these challenges. My first research is high-speed THz phase modulator based on liquid crystal materials. The next project is I introduced high modulation depth THz modulators into the internal reflection geometry. And then I found that the total internal reflection geometry can also be used for achromatic terahertz waveplates. In the end, I also developed a theory to describe the field enhancement effect of metal wire grating in total internal reflection geometry. In the end, I will introduce the THz spectroscopy and material characterization in TI geometry. So the first project is fast speed THz phase modulator based on liquid crystals. I will explain the operation principle first, and then I will introduce a new design of electrode for the fast speed THz phase modulator. Then I will show the experimental results. So the operation principle of liquid crystal-based THz phase modulators is using the birefringence of liquid crystal materials. When the terahertz light passing through a layer of liquid crystal, and in this case, the terahertz light experience ordinary refractive index. In this case, it will experience extraordinary refractive index. So in these two cases, it will have a phase change. And the operation speed of liquid crystal device is limited by the self-relaxation time. We can see it from this equation. The self-relaxation time actually limited is decided by the thickness of the liquid crystal. Actually, that's bad news for our terahertz because terahertz have long wavelengths. So for example, if we want a terahertz quarter waveplate at 2 terahertz, that means we need 190 microsecond liquid crystal. That will give us 2 minutes self-relaxation time. So it's just too slow for real application. So one approach to fast the orientation of liquid crystal molecules is to apply a voltage to generate electric field to help rotate the orientation of liquid crystal molecules. And then we can calculate the operation time using this equation. And based on this equation, we find if we put 100 volt on the previous device, we will have like 0.88 millisecond operation speed. So that's much faster than the previous 2 minutes operation speed. And actually, this kind of idea was used in this publication. But in this publication, they used 2 spacers to generate the in-plane electric field to help rotate the liquid crystal molecules. But because these 2 spacers are so apart, so the distance is so large, so they need 1,000 volt to rotate the liquid crystal molecules. And that's too generous to operate. So our idea is to use some wires in the grating to generate the in-plane electric field. Then we can have a very short distance. We need a very low voltage. And then we propose the design like this. We have 2 pieces of window with grating, and we pick some wires in the grating to generate the in-plane electric field. And the other grating will generate the out-of-plane electric field. So we have electric field for both in-plane and out-of-plane rotation of the liquid crystal molecules. And I run some simulation, and I found that the electric field distribution actually matches with our expectation. And we start fabricating the liquid crystal device like this. We have a photoalignment layer on top of the grating. And initially, we align the liquid crystal molecules vertical to the grating. In this case, when the terahertz light passing through the grating, and it will experience an extraordinary refractive index of the liquid crystal. And in this case is without any voltage. After we put an in-plane electric field, and the liquid crystal molecules will align along the electric field. And when we put the outer plane voltage on, the liquid crystal molecules will be rotated vertically to the gap, and the terahertz house will experience an ordinary refractive index. So we can switch between in-plane and outer plane in these 2 cases. So in theory, our design will give us from the cell-off, that's low voltage, to outer plane, a 70 femtosecond time delay, and that's corresponding to at the 2 terahertz correspond with a phase of 57 degrees. And our experimental results are like this. We can see there is a tiny phase delay in the results, and in these 3 cases, we see the peak-to-peak are similar. So that means in the operation process, we have very low insertion loss. And if we look at the second reflection house, that's more clear to see. And we found that the time delay is 140 femtosecond. So that matches with our experimental calculation, theoretical calculation. So we run an experiment with 250 continuous measurements, and with our THz time domain system, each measurement, the integration time is around 0.33 seconds. And in this figure, every dot represents one measurement. And we can see from in-plane to out-of-plane transition, there is no dot. That means the transition time is less than 0.3 seconds. And in the outer plane, the red dots, in the outer plane to in-plane transition, it takes around 10 dots to finish the transition. That means it takes around 3 seconds to finish the transition. And if we put a no void zone, that's the initial design, the self-relaxation time of the liquid crystal device is around 40 seconds. So that's very slow. And our device improved the operation speed by 10 times. And actually, this kind of design can be used for larger phase modulator. We can stacking several devices together, and then we can get a 30-degree phase change, a 60-degree, and then a 90-degree phase change. Because we can use plastic material such as topaz as a window, and the topaz has a close refractive index with the liquid crystal sample. Then we will introduce very little insertion loss with in the stacking devices. And this kind of device can be used for a THz phase modulator array for the THz beam shifting. So summary to the first project, I introduced a new electrode design, and then I fabricated the device and I measured the performance of the device, and it shows the device has 10 times faster operation speed. And a larger phase change modulator was proposed. The second project is I introduced conductive interface total internal reflection, and I developed a theory to describe the conductive interface total internal reflection, and I designed a silicon dioxide gated graphene device in THz geometry, and then I designed a better performance ion gel gated graphene device in THz geometry. And then I use an optical pumping method to design an optical pump, LED pump silicon device in THz geometry. So one drawback of current broadband THz modulator is the short interaction length between the THz light and the conductive layer. So basically, the THz light just passing through the conductive layer with very short interaction length. And many efforts to improve the interaction length actually bring more problems, such as narrowband operation and high insertion loss. So I was thinking, is there any approach to improve the interaction length without influencing the operation bandwidth? And the attenuated total internal reflection geometry gave me a hint. In the ATR geometry, the total internal reflection happens in the prism and the sample interface. So the evanescent wave will penetrate into the sample and propagate for a short distance. Then I was thinking, how about I put a conductive layer on top of the prism? Then the evanescent wave will pass along the surface and interact with the conductive layer. Then we may have a very high absorption. So to understand this, I compared these two geometries. For ATR geometry, it is a two-layer system, prism and sample. And the prism's refractive index should be higher than the sample. And the thickness of the sample should be higher than the penetration depth of the evanescent wave. For the conductive interface THz geometry, it's a three-layer system: prism, conductive layer, and air. And the conductive layer has higher refractive index compared with the prism. And the conductive layer is optically thin. But both of these two geometries are broadband. And here I want to show that the conductive interface THz geometry is not the surface plasma resonance, because we are not coupling the electromagnetic wave into a matter wave, and it's not based on resonance effect, and it works both for S and P polarization, not only for P polarization. So the next question is, what's the reflection coefficient of this geometry? I started with the modified Fourier equation. This is well known. The modified Fourier equation actually can only describe the incident angle smaller than the critical angle. That's a subcritical case. So I was thinking, how can I derive an equation for supercritical case? And I looked back to the boundary condition and the Snell's law. I found when the incident angle is larger than critical angle, the transmitted wave becomes an evanescent wave, and then the transmitted angle becomes an imaginary number, and then the cosine theta becomes an imaginary number. So I tried to substitute the cosine theta imaginary number into the modified Fourier equation, and I got the new equation in this form. It has imaginary part in this equation, and this is for S polarization. I also tried to derive equation for P polarization, and this time we don't have the existing equation for P polarization, so I started to derive it from the boundary condition. And then I solved the equation and got the result for P polarization with conductive interface. And this for subcritical angle. When the incident angle is supercritical, following the same idea, I replace the cosine theta t into an imaginary number. Now we get the form for P polarization. And I also run simulations to verify my derivation. And the open dots in the figure show the simulation results. It matches with the line theoretical results. So then I was thinking, how can I make this kind of geometry for the THz modulator? If we have non-conductive interface, that's the total internal reflection. So the reflectivity is 1. And if we have super high conductive interface, that's a metal layer, so the reflectivity is still 1. How about we have some conductivity in between? So I use the equation and I use simulation software to get the results. And I found the minimum point here when with the silicon substrate, when the conductivity is 9 millisigma, the reflected intensity is lower than 2% actually. And at the same conductivity in transmission geometry, the transmitted intensity is over 30%, so big difference. And if in the transmission geometry, if we want to get the transmitted intensity lower than 2%, we need 62 millisigma. That's difficult to get. So I designed a modulator like this. We have a graphene device, and I place it on top of the prism. And with our terahertz system, we will have 24 degrees as the incident angle. It's larger than critical angle. So the reflection will happen at the top surface of the silicon substrate, and the evanescent wave will interact with graphene on the top. And thanks to Professor Xu's group in device fabrication, we now have a device. And we modified the gate voltage from negative volt to positive 15 volt. And the experimental results are here. We found with 15 volt, it has a highest peak-to-peak value. With negative 9 volt, it has a minimum peak-to-peak value. So we can calculate the corresponding modulation test with this equation. And we found that in our TLR geometry, we have a 40% modulation depth. Compared with the same device, we only get 15% modulation depth. So just to change the geometry with the same device, we have 3 times higher modulation depth. And I extracted the optical conductivity of that device in transmission geometry, and I compare the reflected intensity in theory and in our experiment at these extracted conductivity, and I found they match quite well. So that means my derivation are correct. Okay, the next step is how to improve the 40% modulation depth. 40% is not enough. One method is to use high conductivity layer. And this can be done by ion gel. Ion gel can heavily dope graphene and can push graphene's conductivity to 5 milliseconds. So I designed an ion gel gated graphene device and using a similar geometry. And we got the experimental results like this because there is a thin layer of ion gel on top of graphene. So in time domain, there is a small time shift. But we can see the peak-to-peak value has a significant change. And the corresponding modulation depth of this device is averaged around 80%. So compared with the silicon dioxide gated device, it's 2 times higher. But further pushing graphene's conductivity to like 9 millisigma is very difficult. So I look back to this equation, and I found actually the reflection coefficient is related to refractive index and incident angle. So I run a series of calculations. I found if we can use quartz as a substrate, we will get a very high absorption, only with 4 millisigma conductivity. But with silicon substrate, we need close to 9 millisigma conductivity. So quartz substrate will make our life easier. So I designed the device with a quartz substrate. And the quartz substrate graphene device gives us the result like this. We can see the peak-to-peak value changes more serious than the previous one. And we can see at a gate volt of 1 volt, we get a modulation depth in a broader range over 90%, and at some point it is close to 100%. And one interesting thing to notice is actually at 2 volt. At 2 volt, the conductivity is higher than 1 volt, but the modulation depth is lower than 1 volt. That's because at 2 volt, the conductivity is around 5 millisigma, and in our theory, the minimum reflection, the highest attenuation appears at 4 millisigma. So the experimental results matches with our theoretical predictions. And we can also see from the time domain pulse. At 2 volt, the peak-to-peak of the time domain pulse actually goes up a little bit. So that introduces the lower modulation depth. But the drawback of ungeogated device is slow operation speed. So how to improve it? Then I look back to the silicon substrate device. In theory, we only need 9 millisigma conductivity. Electrical way is difficulty. And we can use optical way. So optical doped silicon can easily get 9 millisigma conductivity. So I designed the experiment with a laser, optical pumping the silicon substrate in transmission and in total internal reflection. And I can compare the performance of these geometries. So in transmission, the peak-to-peak value doesn't change very much. And in KR geometry, we have more obvious change in the time domain signal. And then we can calculate the corresponding modulation depth. In reflection geometry, we get average modulation depth around 98%. And then we found the interesting thing is that in reflection geometry, the second lowest pumping intensity even outperforms the highest pumping intensity in transmission geometry. So reflection geometry is just so efficient, so better than transmission geometry. And in reflection geometry, actually we don't need a collimated light source, and we don't need a coherent light source. So I replaced the laser diode with a much cheaper light source with a LED light. And with the LED light, pumping the silicon substrate on top, and we get the pumping intensity so far. And I also tried to demonstrate a spatial modulation of the THz light. So I block a quarter area of the light tube of LED light. And in the experiment, we can see when there is low light, so 4 pixels, or show high reflectivity. And when light is on, the blocked area should also still show high reflectivity. But the surrounding 3 pixels, because optically pumped, show low reflectivity. So this design has a potential to be used for spatial modulation for THz. And because the structure is so efficient, and actually it can be used to do more interesting things. So you can see we can manually control THz signal. So everybody in our group can't wait to have tried to tap their phone to manually control the signal. So the summary to this project, I developed the theory for the conductive total internal reflection geometry. And then I designed a solid steady gate graphene device, and it gives 40% modulation depth. Then I designed an ungeogated graphene device in THz geometry. It gives 99% modulation depth. And then I conduct a LED pumped silicon experiment, and it gives us a broadband 100% modulation depth. And it can be used in the future for spatial modulation for compressive sensing imaging. The next project is I explored a metal wire grating in THz geometry to achieve a chromatic polarization conversion. I will first introduce my development of the theory for achromatic polarization conversion in THz geometry. Then I will show a design for a THz wave plate based on metal material grating in THz geometry. Then I developed the design to make it an active device for THz wave plate with vanadium dioxide thin film. In the end, I will introduce a graphene metal wire THz modulator in THz geometry. So after previous exciting exciting project, I can't wait to try any kind of conductive interface on top of our grating. So I found a metal grating from the previous liquid crystal project. The grating area is okay, but the surrounding material cracked it. So I use it and put it on a prism. And firstly, I set the wire vertical to the electric field. I found that the pulse is close to, there is no wire grating. So it's almost like no grating on top. And then I rotated the grating 90 degrees. This time the wire is parallel to the electric field. And I found that the reflected pulse looks like reflected from a metal layer. And you can see the phase opposite. And then I rotated the grating to some angle with the electric field. And suddenly I found the pulse disappeared. So I got a discovery from some rubbish. And then I analyzed the disappear of the signal. I found it's not absorbed or disappeared, doesn't disappear. It's actually because the polarization of the reflected light converted. And then I realized that we can use metal wire grating, and by rotating the grating, we can generate a polarization conversion device. So I analyzed this theory from the boundary condition, and then I derived the equation together with another colleague in our group, Xudong, and we got the equation like this. It's a little bit long, and if the equation is like this. If we have S-polarized light incident, we will get S and P polarization components in the output THz light. The same, if we have a P polarization incident THz light, we will get two components in both S and P directions. Next, we run some simulation. We run some experiment, and we found at the incident angle of 52 degrees, we can have the experimental results represented by the dots in this figure, and the dots matches quite well with the theoretical prediction. When we rotated the grating angle, theta, we can see the change of the reflect amplitude and the phase. And the error bar in this figure represents the distribution of results in the frequency range of 0.1 to 0.7 Hz. So that means our device is achromatic because the error bar is not very large. And in the calculation, we found a very interesting angle. When we set the incident THz polarization 45 degrees to the incident plane, and then we rotated the grating. We found an interesting thing. When the rotation angle is around 34 degrees, in the reflected THz light, there is almost a P polarization. So the 45 degree incident, linearly polarized incident light rotated to an S polarization output light. If we keep rotating the grating, we find at the angle of 58 degrees, the reflected THz light has similar S and P component amplitude, but they have 180 phase difference. That's a halfway plate. So that means the polarization of the output THz light rotated by 90 degrees. And if we keep rotating the grating, when the rotation angle is 90 degrees, we found that the reflected THz light has S and P component with the same amplitude, but this time with 90 degree phase difference. So that's a quarter wave plate. So the linearly incident THz light converted to a circular polarized THz light. And the results are achromatic in the THz range from 0.1 to 0.7. And then we draw the experimental data in this figure, and I found with the same device, we can realize a 45-degree polarization rotator and a quarter-wave plate and a half-wave plate using one single device, and the device is achromatic. But ideally, I still want to design a device can be optical control or electrical control instead of mechanically controlled by rotation. So I was thinking, if we can generate a conductive layer under the grating, then the conductive layer will short connect the grating. Then it will stop the conversion of the polarization from the grating. So vanadium dioxide layer is a good candidate because its phase can be switched between the insulating phase and the metallic phase by changing the temperature. And the temperature change can be realized with the electrical wave. So I proposed the active device like this. We have a silicon substrate with vanadium thin film on top, and then we fabricate the metal grating on top of the vanadium dioxide layer, and then I put it on top of the prism. In the beginning, I rotated the grating to some angle and fixed it. Then the grating will convert the incident THz polarization to some other polarization. If I put the voltage on the vanadium dioxide layer, the vanadium dioxide layer will switch to a metallic phase, so the conversion from the grating will be stopped. It will be the same as initial incident polarization. So I run some calculation with silicon substrate. I found that when the incident angle is 24 degrees, and if I rotate the grating to 47 degrees, and the S-polarized incident light will be converted to a P-polarized THz light. And the amplitude ratio is 10 times to 7. So almost no S-polarized light left in the reflected light. And I run some simulation, and simulation results match it with calculation results. And the incident angle we required is 24 degrees. So that sounds very familiar to me. I remember in the previous graphene experiment, we have a 24 degree incident angle. So that means I don't need to change the setup of the system and just replace the graphene device with the vanadium dioxide device. So that saves me a lot of effort. I was so lucky on this project. And I tried this device in measurement. And I found when I rotated the angle to 45 degrees, in the experiment, the peak-to-peak value of S polarization get a minimum point. That means it's almost converted to P polarization. And I compare the 45 degree angle with 0 degree and a 90 degree results. And I found when the rotation angle is 9 degree and 90 degree, these two results have the similar peak-to-peak value, but opposite phase. That matches with our previous analysis. One is like dielectric interface reflection, one is like a metallic phase reflection. And when there is no voltage on vanadium dioxide layer, the peak-to-peak value is minimum. When we put the voltage on, and because vanadium dioxide is switched to metallic phase, so it the peak-to-peak value of the reflected light recovered. And it looks like the 90 degree results. So that matches with the metallic phase switching. And because the vanadium dioxide layer is not so conductive, it's only just 30 milliseconds. So the recovery is not completed. If in the future we can make a thicker vanadium dioxide layer, it could be recovered completely as a 90 degree case. Then I was thinking, if we put a layer with lower conductivity than vanadium dioxide with the grating, so what will happen? And let's say a graphene layer together with a grating. And actually, this kind of structure was researched, and they use grating together with graphene. And because the grating can enhance the near field electric field intensity in the gap of grating, so the enhanced electric field will strongly interact with graphene and introduce high modulation depth. But still, this is in transmission geometry, and this requires around 5 millisigma to get 88% modulation depth. With that's still not high enough. And the ion gel device actually has very slow operation speed. Then I was thinking, how about we put this kind of grating structure in THz geometry with graphene? To answer this question, and I started with the transmission geometry, and with sub-wavelength metal wire grating is like a polarizer. The electric field in the gap will have a field enhancement. The enhancement factor is eta. Eta equals to the period divided by the gap width. It can be understood by the boundary condition. If we do an integration along this loop, we'll get the result, eta equals to P over gap. And the absorption from graphene is equal to the area of graphene times its conductivity times electric field intensity squared. And in this case, graphene transferred to the grating. In this case, the effective area of graphene actually is smaller because this area of graphene are short connected. So the effective area of graphene in this case is only gap over period. But in this case, the electric field is enhanced by eta times. So the eta should be before electric field. And because this relationship is square relationship, so in the end, still, even with smaller graphene, the absorption increased by eta times higher. But still, this is in transmission. So I start to derive the geometry with this geometry in total internal reflection. And I started with boundary condition and energy conservation. And I expanded the energy conservation to get the result without grating. And I found the absorption part from graphene is actually not related to the incidence angle. So that makes my derivation easier. I put an enhancement factor in the absorption part following the previous idea. And then I can calculate the reflection coefficient with metal wire grating on top of prism. And I found the equation is in this form. This looks very similar to the previous form without grating. But in this case, it has an enhancement factor before the conductivity. That means we can get the same reflection with 1 over eta smaller conductivity. For example, if we get a 20 micron metal grating and with different gap, we will get eta equal to 10, 4, and 2. And in simulation and calculation, we can get these 3 enhancement factors give us similar absorption from graphene. But when eta equals to 10, we only need a conductivity smaller than 1 millisigma. So in this case, previously, we needed 9 millisigma to get a high modulation. Now, we only need 0.9 millisigma to get a high modulation. So this device will give us very high modulation depth. And 0.9 millisigma can be achieved by a solid-state graphene device. With the solid-state graphene device, we will have high modulation depth. And because the metal grating is not based on resonant effect, so it will not influence the operation band. So it is a broadband modulator. And the electrical wave will consume less energy than optical wave. So in all, it's my dream modulator. And this kind of modulator in the future can be used for THz modulation communication, and can be made array for THz comparative sensing imaging. Summary to this project, I derived the equations for metal wire grating on top of prism in THz geometry. And then I realized a multifunctional achromatic THz wave plate. I designed and demonstrated an active THz wave plate based on vanadium dioxide layer. Then I developed a theory and a design for a THz metal wire grating with a THz modulator in THz geometry. The last project is THz spectroscopy and material characterization in THz geometry. First, I will show the THz spectroscopy of alpha lactose in THz geometry. Then I will show the conductive mapping of graphene in THz geometry. So my previous projects are all based on the conductive layer on top of the prism in THz geometry. So I was also thinking, can it be used for dielectric material measurement? And then I proposed 2 setups for dielectric material measurement, one for liquid, one for solid. And I run a simulation for 5 microsec alpha lactose sample, because lactose has 2 absorption peaks in the terahertz frequency. One is 0.53, one is 1.37 terahertz. And I found with a 5 microsec lactose sample in transmission geometry, actually the absorption peak is not very obvious. But if we place it in the, if we change it to TR geometry, the absorption peak is more obvious. And in this case, it can be used for the mechanical recognition of thin film for dielectric materials. But we're still struggling in making the uniform lactose sample, so I only can show the simulation result here. One of the possible application is for connectivity mapping, because we can visualize the small change of connectivity of graphene. In transmission, actually it's not that obvious. We can barely see the connectivity change with different gate voltage. But in TR geometry, we can visualize, it can be visualized easily. We can see the connectivity change at different gate voltage of graphene more easier. So the setup can be used for connectivity mapping for conductive material. Summary of this project, I proposed a thin film THz spectroscopy, and which is sensitive for dielectric material measurement, such as alpha lactose. And the THz geometry can also be used for connectivity mapping for conductive material. So summary of my PhD work. First, I introduced a high-speed terahertz phase modulator based on liquid crystal materials. And I designed a new electrode design, and the operating speed was improved by 10 times higher. And in the future, a phase modulator array can be fabricated. Then I introduced a conductive interface TR geometry. It can be used for terahertz modulators. So I developed a theory of conductive interface TR geometry, and then I designed a graphene device that shows 99% modular depth, and with another way to generate a conductive layer, the optical device showed 100% modular depth in a very broad band range. And in the future, it can be used for comparative sensing imaging. The next project is metal wire grating in TR geometry. I developed the equation for metal wire grating in TR geometry, and realized a multifunctional achromatic terahertz wave plate. And I developed the device to an active achromatic terahertz wave plate with vanadium dioxide layer. And then I developed a theory to describe the field enhancement effect of metal wire grating in TR geometry. And then I proposed the graphene metal wire integrated modulator in TR geometry. And the last project is terahertz spectroscopy and material characterization in TR geometry. I proposed a thin film terahertz spectroscopy, which is sensitive to dielectric material measurement. And also this geometry can be used for conductive material measurement for conductivity mapping. These are my publications. And in the end, I want to thank my supervisor, Emma, and also want to express thanks to Ed, to the people in our group, and thanks to my family. Thank you all, audience. Thank you.
Thank you.